Now we move on to chapter 3, finding and summarizing relationships. In particular, we'll focus on the role of straight lines in data analysis. So to start with, let's talk about the aims of this chapter. We have several aims, and first of all, we're going to introduce, or for most of you, is to review what an equation of straight line look like. And then we'll talk about how to transform some variables so that an equation yields a straight line graph instead of a curved graph. What I mean by that is the graph of many functions are curved. However, we can introduce new variables to make them straight line. We'll talk more about this. And also we're going to introduce a very informal method called black thread method to get an equation of the line that approximately fits the set of plotting points. And finally, we'll define residuals and discuss outliers. All right, to start with, let's look at the following table, and we have the Y value represents the temperature in Fahrenheit from 32 degrees, that's when the water freezes, to 212 degrees Fahrenheit, that is when water boils. And X represents the Celsius that starts from the 0 degrees and goes all the way to 100 degrees. Many of you should be very familiar with this conversion. And if we plot these points, plot X against the Y, and here is what we observe. You see all these points, actually we only plotted the X values up to 70, but we can see clearly a pattern here. All these points are on this straight line. In fact, you can easily find the following information of the line. First of all, you can find the slope. The slope is defined by the rise over run. So to find the slope, we can choose 2 points such as 20,68 and 30,86. If we choose these 2 points, and then we can calculate the rise over run, the Y, the change of Y from 68 to 86 is 18 that is obtained by subtracting 68 from 86. The change of X is apparently 10. So 18 divided by 10, which is 1.8, is the slope. And also the y-intercept is the value of y when x is equal to 0. In this case, when x is 0, y is 32. So we know the slope and we know the y-intercept, and therefore you can write down the equation of the line using the slope and in y-intercept, namely y equals 1.8x plus 32. There is a question some of you might have, that is, for finding the slope, what if we choose a different pair of points? For example, you can choose x equals 10, y equals 50, or x equals 90, y equals 194. Well, the fact is, it is a property of the straight line that it doesn't matter which pair of points you choose, you will always get exactly the same slope. This is not necessarily true, of course, for some other curves such as parabolas or sine curve. However, it is a nice property of the straight line. So don't worry about what pair of points you choose. As long as your points are all on the straight line, you can calculate the slope this way. So in summary, we define the slope of the line that is usually denoted by m, which is defined by the change in y divided by the change in x, or in other words, rise over run. And also the y-intercept, which is usually denoted by b, that is the y-coordinate of the point at which the line cuts the y-axis. Another way to think about it is the y value when x is equal to 0. And finally, once you know the slope is m, and y-intercept is b, you can write the equation of line as y equals mx plus b. And sometimes when we have an equation that is apparently not necessarily a straight line, we can transform some variables so that the new equation becomes a straight line. For example, everyone should know that this y equals x squared. The graph is a problem. It's like a U-shaped thing. It is curved. It is not a straight line at all. However, if you introduce a new variable, let's call it a big X, capital letter X, which equals the big small x squared. And then you can write y equals 1 times the big X plus 0. So this is 1 is the slope and the y-intercept is 0. So now you see the new graph of y versus the big X becomes a straight line and it's no longer a problem. Now let's introduce what we mean by exact formulae. By the way, formulae is a plural form for the word formula. And by the exact formula, we mean a relation that the left-hand side is precisely the same as the right-hand side. For example, A equals pi r squared. The area of a disk is equal to pi times the radius squared. And V equals pi r squared h. This is for calculating the volume of a cylinder. If you know the base radius r and the height h, this is how we find the volume. Or in physics, if something is moving at a constant speed r and it moves for a time t, then the total distance is calculated exactly by r times t. And this c squared equals a squared plus b squared should remind you about the famous Pythagorean theorem that says the hypotenuse squared equals the total of the two legs squared. Those are the exact formulae. And what would be something that's not exact? For example, if I say, hey, the value of pi is approximately 3.14, that's a true statement. However, this does not represent an exact formula. This is not exact relation because the value of pi has infinitely many digits. It's not past 3.14 precisely. It's approximately 3.14. So that wouldn't be an exact formula. All right, let's look at this example from physics. And theoretically speaking, we have the distance equals speed times time. So, but whenever you know the speed, whenever you know the time, you can calculate the distance. However, in real life, if you actually measure the time and also the difference and the distance, and you will see something here. For example, when r equals 5, and theoretically speaking, when time is equal to 1, and the distance should be 5 times 1, which is 5. However, when you actually do an experiment, you might observe something like 5.2. Well, we're all human beings. We all make mistakes. This is not even, strictly speaking, a mistake. This is just some inaccuracy in measuring. So there is a deviation, which is defined as the observed value minus the formula value or the theoretical value. So in this case, the observed value is 5.2 and the theoretical value is 5. So the difference is 0.2. And when t equals 2, again, the theoretical value would be 10. You might observe something like 10.1. Again, there is a small difference, 0.1. Again, this means what we observe is close to, but not exactly equal to the theoretical value. And when t equals 3, the formula value is 15. We might observe 14.8. In this case, the observed distance is actually a little bit shorter than the theoretical distance, which is really okay. And however, we would say the deviation is negative, and which is nothing surprising. The deviation, of course, could be positive, negative, or 0. And this motivates us to give a very formal name for this deviation. We call it residual. The residual is the difference between the observed value and the value estimated from the equation of the fitted line. And this residual could be positive, could be negative, or if you're lucky enough, can even be 0. So there's all the possible values. All right, and of course, some lines do not necessarily pass through the origin, such as in this example, if your body starts 8 feet from the point and goes directly away at a rate of 5 feet per second. So now when t equals 0, the distance is already 8. So now the total formula, the formula for the distance becomes d equals 5t plus 8. All right, another example is the area of a circle. We know that the area of the circle with radius r is a equals pi r squared. In this example, a, the area, is a quadratic function of the radius. It is also a power function. So the graph is apparently not a straight line, it's a parabola. So this is not convenient for our purposes. So to make a straight line out of this relation, we can do one of these two things, not both, just one of these two. Number one, we can define the area as the linear function of r squared. Basically, consider this r squared as another variable. You can call it big R if you like. So a equals the slope pi plus the big R. Times the big R plus 0. Or alternatively, you can also take the square root of both sides of the equation and get the square root of a equals the square root of pi times r plus 0. So now this root a becomes a new variable. It is a linear function of the small r. Either way works, and we can produce different straight lines after using this change of variable. All right, a few more examples. If this relation is y equals 3x squared plus 2, this is apparently a quadratic relation. And you can define t equals x squared, and then y becomes 3t plus 2. Or this is a little bit tricky. If y equals 2 divided by the square root of x. And well, there's nothing too tricky about it. We can simply set a new variable. Let's call it t again. You can call it u, you can call it v, you can call it anything you like. Let's just call it t for now. And if you set t equals 1 over x, the square root of x, and then y becomes a linear function of t, y equals 2t. And the third one is a little bit tricky, and let's just write down some details. If y equals 3 times 10 to the power of x. So this is the relation between y and x. And what we can do is to take the common logarithm, the base 10 logarithm. And so I'm using this notation log y and to refer to the base 10 logarithm. This is different from how this log is defined in R. And so we take the log of the right-hand side, 3 times 10 to the x, and record that the logarithm of the product of two numbers is the total is the sum of these two logarithms. So it's log 3 times or plus log 10 to the power of x. Well, because the log function and the exponential function are inverse of each other, the second term is really simplifies to x. Another way to think about this is this expression is asking, hey, we raise 10 to a certain power. What is this power to get 10 to the power of x? And well, of course, the answer is x. We raise 10 to the power of x to get 10 to the power of x. And so the second term, this expression is precisely x. And therefore, what you can do is to define a new variable, let's call it z, and as log of y, and this z becomes a linear function of x. That's equal to x plus log 3. Let's look at this example of the planets and their distance from the sun. Of course, when we measure the distances in the universe, you got to choose the unit carefully. And if you use miles, and the number is going to be huge. So in this particular example, we'll use the distance as 1/10 times the distance between the Earth and the Sun. So in this case, from the Earth to the Sun, the distance becomes 10 because by the definition of our unit. And of course, technically speaking, the asteroid is not a planet, and the Pluto is maybe no longer a planet by the newer definition, but we don't worry too much of that by our purposes. So we can have a table like this, and you can probably observe as it increases, this dn, the distance between this planet and or asteroids, will increase. However, it's hard to see how it increases until we plot these points. So when we plot these points, And one direct observation is that this point seems to be going up in a curved way. So if this is your observation, you probably shouldn't try to fit a straight line into the data because the pattern is not linear, or it does not looks like to be linear. Instead, you probably should try something else. So here, if you take the common logarithm of all the distances and plot those against n, and here's what you get. You see, now these points looks much closer to a straight line. There is a straight line that seems to fit the data pretty well. Well, you may say, hey, wait a minute. A lot of points are not technically on this line. That's true. That's very true. However, our goal is not to find a line that passes through all these points. Such a line does not even exist. Our goal is to find a line that fits the data really well in the sense that most of the points, all the points are really close to this line. We'll make this idea more precisely defined in later chapter, in chapter 11. But for now, just keeping this in mind, that this is the goal. We're going to find a line that will fit the data really well. And later we'll talk about how to find the equation of this line. And this particular line is given by y equals 0.233x plus 0.330. So this line would fit the data really well. And another example is as we go down, as we go below the Earth's surface, the temperature actually goes up. So if you measure how many meters we are below the surface, and also we can measure how many degrees above the, how many degrees increases. And we can see that 40 meters below the ground, the degree raised 1.2, and also 150 meters below the ground, the temperature raised by 4.7 degrees, and so on. Now, to find a relation between these two, again, we plot the data. This is what we get. And now we try to fit the line into the data. This line does not pass through these points, and however, it does give you a reasonable job in fitting the data. Notice that in this line, we choose a line. In this case, we choose a line with the y-intercept is 0, because when x is 0, and the y value should be 0, because basically it's saying we are at the surface of the Earth, of course, the temperature will be the same as the temperature of the Earth. So that's why we choose this specific line, and y equals 0.039x is the line that we choose to fit the data.